Okay, welcome to lab here. So as I mentioned, we're going to continue on a little bit more about organic, and then we'll talk about all the remaining stuff at the end here. So earlier here, we were talking about sort of different organic compounds. Again, you could classify different organic compounds based off of their functional groups. Um, and we kind of got into alkanes here and sort of naming alkanes. So the basics of what we sort of went over, a few of those examples, is you always want to find the longest continuous carbon chain. It doesn't have to be the straightest. It could go up, sort of over, and all that. The only thing you can't do again is kind of go backwards. Once you do that, that's really going to be the base of your name. Once you do that, you then will most likely have some groups that are attached to that main chain, but are not really part of it. And again, a lot of times those are referred to as alkyl groups, and they also are based off of those first 10 alkanes. We usually will drop just a hydrogen off of those guys to allow them to be able to connect in and not have too many bonds. But again, we name them kind of with a YL. So again, a one carbon group would be a methyl group, a two carbon group would be an ethyl group, three carbon would be a propyl group. A couple of groups that I didn't mention that also is named as groups are the halogens. So what we're talking about that right now. If you have somebody from group seven, so you have like a fluorine, a chlorine, a bromine, an iodine, those are named kind of like what they were in sort of coordination compounds, which is like fluoral, chloral, bromo, iodo. Those are how we kind of name our halogens if they're attached. Um, we want to name all the groups. We then want to number the longest carbon chain. And you usually have two options, either kind of left to right or right to left. And the way you choose which way you want to number is whichever way gives the groups the smallest number. So we're always looking for the smallest number for those groups and alkanes. And again, whichever way will give you the smallest numbers, the way you want to name it. Then you want to basically just give the location of where all the groups are. Again, a dash between a number and a letter. If you happen to have two numbers together, you put a comma between them. If you have more than one of the same group in a compound, you use other prefixes like di for two, tri for three, tetra for four. Any questions on any of that stuff there that we talk about? All right, so why don't you try some here? To the right is sort of the condensed form, and I kind of drew the line structures for these guys next to them, so you could kind of see what those would look like. So you might want to try to name it from the line structure. You could also look at the condensed structure to help you. So again, try to follow the steps: longest carbon chain, figure out what groups are attached, and again the locations, and then try to put them all together. So I want to take a few minutes and see what you come up with, and then we will talk about it. We got one, two, three, four, five, six. So that's not too bad. Um, if we then go maybe straight across, one, two, three, four, five, and go up, we also get six. We could go maybe right, one, two, three, four, and then up, five and six as well. So it looks like kind of no matter which way you go, you end up with six. So again, there might be multiple ways that get you to the same number. Um, it doesn't really matter which way you choose. It should probably get you the same number or name when it's all said and done. I'm gonna usually always like to take the straightest, so might as well just go straight across here. So if we were doing our line structure, it'd be one, oops, maybe we got one, two, three, four, five, and six coming across that way would represent that. So the basis of our name here is six. So six carbons, all single bonded. The base of the name is going to be hexane. At this point, we then have a couple of groups attached. We got a methyl group here, which is this group right here. And it's a one carbon group, as you can see. We also then have another group attached there. Which is a two carbon group right there. Two carbons is based off of ethane, becomes an ethyl group, and that would be this group right here. Any questions on longest chain, sort of location of everybody? So really, at this point, we want to number. Again, we have two options. We could go left to right, which means this would be carbon 1, 2, 3, 4, 5, and 6. Going in this direction, we would have groups at carbon number 3 and carbon number 5. If we chose to number in the opposite direction, this would be, say, carbon 1. I can't really see it with that color. Let's try a different color then. Let's go with, we'll go with reddish. This would be carbon 1. This would be carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So sort of going in our red direction, we would get a group at carbon 2 and a group at carbon 4. So remember, we're going for the smallest number. So again, it is as simple as 2 is smaller than 3. So we would want to go in the red direction, and we wouldn't want to number in this direction. Again, that's going to give our groups the smallest number. So we see going in the red direction, our methyl is at a 2, our ethyl is at a 4, and now putting it all together. So again, we would want a number in this case 1, 2, 3, 4, 5, and 6. Coming this way, then putting it together alphabetical first. That means that E comes before M. That's going to give us something like 4 ethyl dash, what we got there, 2 methyl hexane. Hey, put it all together, not too bad there. Any questions on how we got to that name there? Okay. Looking at our next one here, we want to find the longest carbon chain. And you may be tempted to just go straight like this, 1, 2, 3, 4, 5. But we do have some guys coming down this way, 6 and 7. So this all is one continuous carbon chain coming around that direction there. And I think that's going to probably give us the most. Our only other option maybe start at the bottom here and come up. So 1, 2, 3, 4, 5, and 6 if you kind of came up that way. And then I think that's, you go this way, 1, 2, 3, 4. So looks like that, was it 7 I counted there a second ago? I think it's 7. Looks like the longest continuous carbon chain. So, and again, that would be on our line structure as well, even though it may look like, is something else attached. This would be 1, 2, 3, 4, 5, 6, and 7 happening there. And base of our name from 7 is going to be heptane. That means we have one group attached right there, and that is a methyl group. And that would be this little line that's hanging off there. We then want to number it whichever way is going to give us the smaller number. And just looking at it, you probably can see going right to left here. 1, 2, 3, 4, 5, 6, and 7, which would be going 1, 2, 3, 4, 5, 6, and 7. Would give us a smaller number. Again, if we went this way, 1, 2, 3, 4, 5. So that would give us obviously too large of a number. So that means our methyl group is at carbon 3. So that is going to turn this into 3-methyl heptane. All one word. I just space it out a little bit there. Any question on that particular name there? All right, then looking at our last one, which looks like a weird one there with our line structure. But let's see if we can figure out our longest carbon chain. Again, continuous longest carbon chain. Well, if we just go straight across, we got 1, 2, 3, 4, 5, 6. Doesn't seem too bad. So 6 so far. If we go across, so 1, 2, 3, 4, and then up 5, 6, 7. That seems more, so that's a little bit better. So 7 so far is a winner. Well, we do have some other options. Let's see. We could go 1, 2, 3, 4, 5, 6, 7. So that is another option. And lastly, perhaps one last option would be to go 1, 2, 3, 4, 5, 6, 7, and 8. So that seems like the most here, which is 8. And that actually is our longest continuous chain. So on our line structure should be 1, 2, 3, 4, 5, 6, 7, and 8 coming that away. That means that we do have a couple of things hanging off of it here. We have a 2 carbon group right here, which would be this group. 2 carbon group is an ethyl group. We also have a 1 carbon group hanging off of here, which would be our line over here. And 1 carbon group is a methyl group. Any questions on sort of that picking there? So now we do have a couple of options in terms of numbering. So we'll go this way first here. We'll start up on top. 1, 2. That's going to be 3. That would be 4. That would be 5. That would be 6. That would be 7. That would be 8. So going in that direction, we end up with a group at 3 and 5. And if we number in the opposite direction, let's use a different color here, maybe. We'll try that. We'll go this way first. So this would be 1, 2, 3, 4, 5, 6, 7, and 8. So going sort of in the black direction here, it looks like 4 and we got there 4 and 6 in that particular case. So what we want to choose is the lowest number. And again, 3 is lower than 4. So we would want to go in the red direction in terms of our numbering. Any questions in terms of that? So going in the red direction, and actually, I'll just go back to the other color, easier to see. And we were numbering in this direction here. So this would be 1, 2, 3, 4, 5, 6, 7, 8. That means that at carbon number 3 would be our methyl group. So carbon 3 would be our methyl, and carbon 5 would be our ethyl. The longest chain is 8. So the base of our name is octane for the longest carbon chain. We want to go alphabetical, which means actually the ethyl will come first, even though it has a higher number. So that would be 5 ethyl. Again, alphabetical regardless of number. 3 methyl. Try to squeeze it all together. Octane. Any questions on that name there? Any questions in general on how to name any of those there? All right, so why don't you try another one here? I think got somewhere maybe. Yeah, why don't you try this one? I think that should be different. Okay, so let's take a look and see how we're doing. So again, here we want to look for the longest continuous carbon chain. So always good, maybe just start straight across. We got 1, 2, 3, 4, 5, 6, 7. So that doesn't seem too bad. If we go perhaps 1, 2, 3, 4, 5, come up 6 and 7. That's not too bad either. But I think there is actually a bigger option there, or longer option. So let's see if we can figure that one out. You could go 1, 2, 3, 4, 5, 6, 7. We could go this up. So let's see. All right, so let's see. We went straight across. We went straight and up. Or our option perhaps is 1, 2, 3, 4, 5, 6, and 7. So it is looking like 7 is our longest. I think that's right. Let's see. 1, 2, 3, 5, 6, 7. Yeah, so it looks like 7 is a winner here. So might as well just take the straightest 7 that we could get. Thinking I saw 8 a minute ago, but maybe I was mistaken. So might as well just take the straightest 7. So we'll just go straight across then. So that's going to give us 1, 2, 3, 4, 5, 6, 7. So on our line structure, 1, 2, 3, 4, 5, 6, and 7 coming across there. That then leaves us 7, which the base should be heptane in that particular case. We also then have a 2 carbon group here. That's going to be an ethyl group, and that would be this guy down here, by the way. We then have a 1 carbon group, which is a methyl here. And we have another 1 carbon group, which is a methyl here. And that means we have 2 methyls, so we got a dimethyl situation happening. We also have 1 ethyl, obviously. So we need some numbers. So if we go left to right, we got 1, 2, 3, 4, 5, 6, and 7. That means going left to right here, we end up with a group at 2. We end up with a group at 3, and we end up with a group at carbon number 5. We went the opposite way. We got 1, 2, 3, 4, 5, 6, 7. So right to left, we have a group at carbon number 3, it looks like. Carbon number 5 and carbon number 6. So those are larger numbers. So we would want to number left to right. So we would want to go with the bottom set of numbers there. And that pretty much going to help us figure out everything that we need. All right, so highlighting this guy straight across. So putting all that together, that means at carbon for our dimethyls, we have 1 at 2 and 3. So that's going to be 2 comma 3 dimethyl. We then would have a 5 ethyl. And in this case, we would go, we'd probably go 5 ethyl, 2, 3 di, as I run out of room, methyl, heptane. Again, alphabetical, regardless of prefix. So E before M here. So that's why we kind of went that way. And we would end up with something like that. Any questions on that particular one? All right. Let's see. We did a couple of those. Why don't we actually let's do some names to formulas. So why don't you draw the condensed formula, and why don't you draw the line formula for this? For each of these. So why don't you give it a try? I'll give you a hint. In doing so, the best way to do it is to work backwards with the name. So work backwards with the name and see what you come up with. So why don't you try it, and then we'll talk about it and see what you come up with. So kind of work backwards in the name. Start with the basics. Actually, here, let's just do one here together just so you get an idea. Let's just say we had, so we'll just name this guy real quick. So we have 1, 2, 3, 4, 5, 6, 7. So that's going to be heptane and 3-methyl heptane. So let's say we had 3-methyl heptane and we want to draw sort of the formula for it. What you want to do is kind of work backwards. So what I mean by that is we would start this way, And heptane tells us that basically we have 7 carbons. So you would start with just the 7 carbons, really nothing else. And that basically takes care of the heptane part. 3-methyl means that we have a methyl group on the 3rd carbon. And since you are drawing it, you have the option of either numbering your carbons left to right, or you could number them right to left. So it really is your choice because you are drawing it. So it doesn't really matter whichever way you go. So in my particular example here, I'm going to assume I'm numbering left to right, which means if I did number left to right, my number 1 carbon would be on the left. So this would be number 1 carbon, number 2 carbon, number 3 carbon. And at number 3, I would put my methyl group, which would take care of that. At that point, everything else here is going to be hydrogen until carbon has 4 bonds. And what that means is the carbon on the far right has 1 line coming in, which means it has 1 bond. That means it needs 3 hydrogens to get to 4. The carbon next to it has 2 lines coming in, which means it has 2 bonds. It then needs 2 hydrogens. Guy next to it also has 2 lines coming in, needs 2 more hydrogens. Also 2 lines coming in, he would need 2 hydrogens. This carbon now has 3 lines coming in, which means it has 3 bonds. So to get to 4, it just needs 1 hydrogen. The guy next to it has 2 lines, which means he would need 2, and he would need 3. This would be the condensed formula for 3-methyl heptane. If I wanted to draw the line structure for it, again, you would follow the same approach. Heptane means I need 7 carbons, so you would draw a line structure that has 7 carbons. Again, 1, 2, 3, 4, 5, 6, and 7. And again, you wouldn't put the circles, obviously. You would do the same thing. You could go left to right, and this could be carbon 1. You could go the other way and go right to left and making that carbon 1. I'll do the same thing as I did before. So this would be carbon 2 here. This would be carbon 3. And that's where I would want to put my methyl group. So what I would do is, since it is line structure, remember, we really don't write anything in unless there is something at the end of the line. So that would be just a line coming down, again, indicating that there is a carbon at the end of that line, which would be a CH3 group. So the line structure for this would look something like this. Any questions on that? So really drawing the structures are a lot of times the easiest because they kind of tell you what to draw. And it's always good to kind of work backwards. So sometimes it's good to work with the condensed formula there, just the carbon skeleton, add all the groups, and then fill in all the hydrogens. Any questions on how to do that? Okay, now that you've seen one done, give that a go on these 3 here. So draw both the condensed formula and also the line structure for each of these. So take a few minutes and see what you come up with. Again, follow that same approach, kind of work backwards in the name. So when we see butane, that should automatically tell you that that should be basically 4 carbons in a row. So if you're going to do the condensed structure, just lay up kind of 4 carbons with nothing else there. That takes care of that. Dimethyl means that we basically have 2 methyl groups attached. They are located at carbon 2 and carbon 3. So again here, since you are drawing it, you could call the carbon on the left carbon 1, the carbon on the right carbon 1. It doesn't really matter. So I'm going to go call the guy on the left here carbon 1, which means that this carbon here is carbon 1. Next to it would be carbon 2, which should have a methyl group. So I'll put my methyl group in there. The next one to that should then be carbon 3. And just to mix it up, I'll put my methyl group on the bottom. It doesn't really matter. You can put it up on top. You can put it on the bottom. It's all the same. Now, that takes care of this part of the name here. So what's left is to make sure all the carbons have the proper number of bonds. So that means we're going to fill in our hydrogen. So guy at the end has only one line coming in, which means he needs three hydrogens. The guy over here has one, two, and three lines. So he needs one hydrogen. The guy here has one line, two lines, three lines. He needs one hydrogen. And the guy at the end has only one line. He needs three hydrogens. So this would be our condensed formula. If we were doing our line structure, you would follow the same thing. So butane would tell you need kind of four zigzag guys until you get four carbons, which would look something like this. Again, one, two, three, and four. And same thing, I'll go left to right just like we did there. So this would be carbon 2, which would have a methyl. So you would just draw a line. And this would be carbon 3, which you would just draw a line. Again, you wouldn't put the little circles at the end, but it would look something like this. Any questions on that particular one there? All right, so rolling to the next one, we're going backwards here. We have heptane, which is 7 carbons. That's a lot of carbons. All right, so we'll go 1, 2, 3, 4, 5, 6, and 7, hopefully. Now we have an ethyl group, and again, an ethyl group is a 2-carbon group at carbon number 3. So I'm going to go left to right again. So this is going to be 1, 2, 3. Since I don't have a lot of room up on top, I'm going to put it on the bottom. So I will do my 2-carbon group here, and that would be my ethyl group at carbon 3. Since I called that carbon 3, carbon 2 must be 1 behind it, and that has a methyl group. And I'll put it here. So that takes care of that. That takes care of that. Everything else going to be hydrogens. And again, this guy would need 3. This guy would need 2. We would need 2 here, 2 here, just 1 here, just 1 here, and just 3 here. Again, the goal here is to get carbon to 4 bonds. Again, you could put the ethyl group up on top, you could put the other methyl group on the bottom. It doesn't matter as long as they're on that carbon in this particular case. For our line structure, again, we would do the same thing. Start with 7 in a line structure form. So I should probably be counting 1, 2, 3, 4, 5, 6, and 7 if I did that right. So 1, 2, 3, 4, 5, 6, 7. Again, going left to right here, this would be carbon 1, this would be carbon 2, right here would be carbon 3, and we have an ethyl group, which would look something like this. Again, 1 and 2 coming off, and at carbon 2, we would have a methyl, which would be straight up there. Any questions on that particular one?
Wouldn't there be ethyl before methyl?
Yeah, it should be in this particular case. That's usually how you do it. I copy these from my book. I think it came from some book. So sometimes people will do that backwards, but the correct way is alphabetical. So the correct name should really be for this particular one 3-ethyl, 2-methyl heptane in this particular case. Yep. And sometimes you'll see that sometimes people are just trying to make up names, so they kind of do it that way. But the other thing that you also sometimes see is after you have a name and you draw it, you may then go to name it yourself, and you would actually name it something different. So sometimes that happens. But you are correct. Like we talked about, really the correct name here should be the 3-ethyl first, and then the 2-methyl, heptane at the end of it. Alphabetical here should go first, regardless of number. Other questions? Okay. So looking at our last one here, again, we would want to kind of follow the same sort of procedure. So we got pentane working. So that is 5 carbons. We'll go with 1, 2, 3, 4, and 5. So that takes care of that. We have 4-methyl. So again, I'm going to go left to right in my case. So 1, 2, 3, 4. We're going to lay up a methyl group there. And 2-chloral, again, going left to right because that's the way I chose the number. Chloral is the way we name chlorine. So remember chloral, bromo, fluoral, iodo for are halogens. And again, everything else here will be hydrogen. So we need 3 there. We need 1 there. We need a couple there and 1 there and 3 there. And again, in terms of our line structure, we will start out with our base of 5. Very badly drawn there. 1, 2, 3, 4, 5, and I added an extra one. Maybe that's why it's badly drawn. Try that again. All right. Okay, so 1, 2, 3, 4, and 5. There we go. And at this point at 2, we would have, again, a Cl. We do want to write the Cl in here. If we left it as just a straight line like we did here, that would imply it's a methyl group. So if there is something other than a methyl group at the end of a line in a line structure, you do have to write what it is. Otherwise, people will assume it's a methyl group. So that's why the Cl is there. And then what we got there for methyl. So 1, 2, 3, 4 would be here. Any questions on how to draw formulas from names? That's the best way, like I said, work backwards, kind of start with the skeleton and then kind of put everything in. The nice thing is if you're drawing line structure, you actually don't have to worry about going back in and sort of putting in the hydrogens. Any questions on any of those there? Okay. So let's get that. Not worry about that. Let's talk a little bit about cycloalkanes and sort of how we name these guys. We got a little bit into it earlier. Again, these are guys that are closed structures, usually sort of given in line formula, and they are also missing a couple of hydrogens from your normal alkanes. And again, the missing of the hydrogens because we basically closed up the ring. So we had to lose 2 hydrogens to allow that bond to happen so that we really don't go over the octet rule there. These are usually our geometric shapes, as you can see here, triangle or square. We name them the same way as alkanes. The only difference is we put cyclo in front of it. So again, this is 1, 2, and 3 carbons, which is based off of propane. Because it's a ring structure, it becomes cyclopropane. Also here, 1, 2, 3, and 4 carbons based off of butane. Also a ring structure becomes cyclobutane in this particular case. We saw earlier as well, these other 2, this is cyclopentane, 1, 2, 3, 4, and 5 carbons, pentane in a ring structure becomes cyclopentane. And then obviously our 6 here, carbons. And again, not usually drawn in, obviously, like we've been talking about, there are hydrogens at each of those carbons, and that is our cyclohexane. Again, 6 carbons based off of hexane in a ring structure, giving you cyclohexane. Not to be confused with benzene that we saw earlier. So benzene ring has the double bonds in it. So this is benzene, different than cyclohexane. So no double bonds in our cyclohexane, double bonds in our benzene ring. So when we name these, pretty simple. If there's really nothing attached, you do just pretty much name the ring and what it is. If there is basically one group attached, you basically just name the group and the name of it. So, if you had, your triangle here with a line hanging off of it. Again, the main part of this would be our triangle, which is basically our cyclopropane. And what's hanging off of it is a methyl group. So this would be methyl cyclopropane. You don't have to give a number for that group because it is what is referred to as being mono-substituted. There's only one group attached. And wherever that group's attached, because there's only one, it's assumed that is carbon number 1 in that ring. So because there's only one group attached, you don't have to worry about giving the name, the number of where this is. It's assumed to be carbon number 1, again, because there's basically only one group attached to it. And if you had it kind of drawn like that, or, if you had it over here, or if you had it like over here, although they may appear different to you, This then would be carbon 1 in this case. This would be carbon 1 in this case. They would all be named the same, even though it may appear different to you. Because there's only one group, that group gets the priority, and that group would be the first carbon. And you don't need to name it because of that. Now, if you do have sort of more groups attached than just one, you do have to give the location. So we would start out here looking at something like this, where we have a methyl group. We have a 2-carbon group here, and that's an ethyl group. And then obviously we have our ring structure here, and that is a 6-member ring, and that would be, as we see here, cyclohexane would be the base of our name. But because there is multiple groups, we do want to number. And since ethyl should come before methyl here alphabetically, we have 2 options as to how we could number this. We could start at the ethyl and go counterclockwise, and that would give us the ethyl at carbon 1 and our methyl at carbon 3. The other option would be to start at the ethyl and go clockwise. This would be 2, 3, 4, and 5 if we went clockwise. And that would give us a 1 and 5 situation, which again is a larger number. So in this particular case, we would want a number in this direction. And the name that we would want to come up with on this guy would be 1 ethyl, again, alphabetical. And then what do we have there? 3 methyl cyclohexane. So if you do have more than one group attached, again, you do have to give that location alphabetically, whichever way sort of gives the smallest numbers. Doing that is the way that you would want to go. Questions on that? And obviously, as we can see here, if there is just one group attached, no need for the number. So this is a methyl group, and that would be methyl cyclohexane. This is a butyl group. I'll spit it out there. That is a 4-carbon group, and that's a butyl cyclopentane, again, carbon number 1. And again, sometimes this may be drawn sort of in line structure as well, all the way through, including the groups attached. So, that first one may look something like this, which again, nothing at the end of that line is a methyl group, which this guy would be this guy. You may also see, the other guy drawn. What we got there? It's a butyl group. Something like this, where we would have 1 carbon, 2 carbons, 3 carbons, 4 carbons. That would be our butyl group. So again, you can have the whole thing drawn in line structure as well, even the groups attached. Any questions on that? Okay, so as I mentioned, if you do have multiple groups attached, we want to give whichever way you need to go, either sort of clockwise or counterclockwise, to give that group the smaller number. So here we would have 1,3 dimethyl cyclohexane, and that would be starting at this guy and going clockwise gives us a 1 and a 3. If we went the other way, 1, 2, 3, 4, and 5. Again, that would be 1 and 5, which would be a larger number. So again, you could go clockwise, you could go counterclockwise. Again, whichever way gets you that lower number. And this is sort of what we were just doing a second ago, I believe. We have 1 ethyl, 3 methyl cyclohexane. Again, we wouldn't want to go 3 and 1, or we wouldn't want to go sort of, that opposite way like I was numbering before. 1, 2, 3, 4, 5, or anything like that. Again, that's going to give us the lowest set of number for our ethyl and our methyl in this particular case. Any questions on how to name cycloalkanes? So a lot of obviously alkanes and stuff like that is in oil type products, petroleum type products. Petroleum is basically just a very long chain of carbons and hydrogens bound together. That's how we get things like gas. They do a thing known as fraction or fracking, where they basically sort of break it apart. So you have these really long chains, and then they bust it up into smaller chains, like gas, like octane, right? Octane, right? 92 octane, 91 octane, 87 octane, right? Octane being basically 8 carbons, right? So it breaks it off into sort of a smaller sort of product in that process. Now, some of the properties of alkanes, because they basically are all carbons and carbons, and that's obviously a nonpolar bond. Carbon and hydrogen is also a nonpolar bond. Again, if you took the electronegativity difference between those, that's like zero point 0.4, which is considered nonpolar. They again are going to exhibit very weak intermolecular forces. They're essentially going to be using those dispersion forces or London dispersion forces, which are relatively very weak intermolecular forces between things. And as I mentioned earlier today, the result of that is you get things that have very low melting points and boiling points. So you expect alkanes and hydrocarbons to have very low melting points and boiling points. And that's also why they're typically, a lot of the smaller ones are gases at room temperature. Even larger ones are liquids at room temperature. Again, they don't have really a lot of association from between them. They also have very low boiling points and stuff, which is why a lot of organic guys are volatile, right? They go into the gas phase very easily. They're also going to be insoluble in water because water is pretty much polar, right? And water is going to try to use hydrogen bonding to interact. So you got something using hydrogen bonding and something using dispersion forces. That doesn't work. Perhaps you remember a famous saying about solubility, the idea of like dissolves like, which means that if you take something that is sort of ionic and polar, they're all good together. If you take something that's polar and polar, they will be soluble in each other. If you take something that's nonpolar and nonpolar, also will be soluble in each other. So all these guys are soluble in each other, basically. Only problem a lot of times is if you take something that's polar and you try to mix it with something that's nonpolar. Again, the reason that's not going to work is because they're both using different intermolecular forces, and they have no long way. I'll say that again. No long way or long term way to basically keep that interaction behaving and interacting with each other. So they may mix for a short period of time, but over a long period of time, they are going to separate out. So if you think about something like, say, oil and vinegar salad dressing, right? You can mixes for a short period of time. You leave the bottle of dressing. At some point, you see everybody separating out into their sort of different layers. And that's typically what happens with alkanes and water. If you've seen an oil spill, for example, in the ocean, the oil tends to float on top of the water. And you usually will get two different layers where you have sort of your organic layer up on top and your water or aqueous layer on the bottom. So they typically will separate out from each other because of those differences. So alkenes, a lot of hydrocarbons have very low melting points and boiling points. Um, and again, that's different than, as you can see here, boiling point increases as you go to the right. Although they're all alkanes, also something that you might remember as well in terms of dispersion forces is it increases with increasing molar mass. So the idea behind dispersion forces, if you sort of remember, is they basically occur from potentially electrons sort of distorting themselves. So electrons moving from one side to the next. That's something is known as polarizability. And that when that occurs, it creates in a nonpolar molecule, just so we're all clear, a nonpolar molecule means that there is sort of equal sharing of electrons over the entire molecule. There really is, you could kind of think of it as a neutral molecule. There's no positive side our negative side. And that's different than a polar molecule, where as a whole, there's unequal sharing of electrons. And what that creates is a positive side of the molecule and a negative side of the molecule. So when we have dispersion forces and they create these temporary sort of attractive forces, it increases with increasing molar mass. And that's because when we have something like hexane, there's more atoms. More atoms means more electrons. There's a greater opportunity for those electrons to basically move around and create those temporary charges than there is down here with butane, which has less atoms, less electrons. So there's a greater chance of polarizability and also greater area for interactions to occur on once you get larger boiling points or larger molar mass. So even though these all are using dispersion forces, hexane would have the higher boiling point because it's larger, more electrons, more chances of interactions basically to occur. Any questions on that? So just since we have this up here, a reference, if you have alkanes, which are essentially all your carbons, very nonpolar, but you can get something, like an alcohol, for example, that has that OH group. That OH group allows it to hydrogen bond, just like water will hydrogen bond. And what will happen in that particular case is you'll actually see alcohols have a much higher boiling or melting points than, say, alkanes because of its ability to hydrogen bond. And just so we're clear as well, when we talk about intermolecular forces, there's really three three types really. There is hydrogen bonding, there's dipole dipole, and there's dispersion forces. Dispersion forces is the weakest, hydrogen bonding is the strongest. The differences between this is typically our dispersion forces is for our nonpolar molecules. Dipole dipole is for our polar molecules that cannot hydrogen bond. And our hydrogen bonding is for polar molecules that can hydrogen bond. Right? By the way, hydrogen bonding is a bond between hydrogen and an electronegative atom like nitrogen, oxygen, or fluorine, right, in order to be able to hydrogen bond. So when we get to something like an alcohol, and especially, you know, sort of smaller alcohols, because they have that ability to hydrogen bond, they typically have very much higher boiling points than, say, alkanes. Actually one of the only guys that could actually even beat an alcohols is almost the strongest in terms of our highest in terms of boiling points and melting points. The one that actually could beat it though is a carboxylic acid that we talked about before. And a carboxylic acid, if you remember, I'll just draw it in the middle here, has this functional group. And the reason why it actually will have the highest out of all of them is it's got like two places where hydrogen bonding could happen. Hydrogen bonding could happen here. And although this cannot hydrogen bond with itself, when another carboxylic acid is around, there could be hydrogen bonding between another one and it. And that creates almost 2 points where hydrogen bonding can take place. And what that does to something like a carboxylic acid is it actually is one of the few things that will have a higher boiling point than, say, an alcohol, because it kind of has the ability to make sort of dimers when that happens, and actually do sort of a double hydrogen bonding for every molecule, as opposed to an alcohol, which can only kind of usually sort of hydrogen bond in one location. So just a sort of a very simple overview of sort of boiling points and melting points. Really, the stronger the intermolecular forces that you have happening between a molecule with itself, the higher the boiling point is going to be. And in terms of organic chemistry, at sort of the lowest end of that, we have alkanes, alkenes, alkynes, really all of our hydrocarbons, because we're pretty much dealing with nothing but nonpolar interaction, and that's dispersion forces and very weak. As opposed to, if you get sort of to the other end of the extreme, we have things like alcohols, which can hydrogen bond. They typically have very high boiling points and melting points. We also have carboxylic acids, which have very high uh, boiling points and melting points because they could definitely hydrogen bond. And in the middle we have other groups like aldehydes and ketones. We have these other very badly drawn groups like aldehydes and ketones. Sort of below our alcohols and stuff like that, ethers as well. Those guys can't hydrogen bond, but they do have a polar group on it between, say, the carbon and the oxygen. So you get those guys kind of like in the middle. Any questions on sort of boiling points, melting points? Again, really tied to intermolecular forces and the strength of those intermolecular forces. Again, the stronger the intermolecular force, the higher you would expect the boiling point and melting point. The weaker, the less you would be. And that's really because when we talk about intermolecular forces, it is really, the force that holds, say, these two molecules together. And all intermolecular forces are basically electrostatic, which means it's basically the simple attraction between the positive side of one and the negative side of another is basically that intermolecular force. And when we talk about, say, melting points, boiling points, that's when we have to break this bond, right, to allow them to go off. So, for example, at the boiling point, that bond would have to be broken to allow this guy to go off into the gas phase, this guy to go off into the gas phase. And the weaker that attraction is, the less energy is needed to do that, less energy needed to do that, the lower the boiling point would be. The stronger that attractive force is, the more energy would be needed, and the higher the boiling point would be. Any questions on that? Okay. So let's talk about a couple of reactions that alkanes actually undergo. The first one is one you probably are familiar with. It's a combustion reaction. Combustion reaction in organic sense is typically a organic guy plus some O2, and it usually will always produce CO2 and water. So carbon dioxide and water, that's your classic combustion reaction, an organic combustion reaction. In reality, a generic definition of combustion is just simply there's O2 involved, but this is usually the reaction most people are thinking about when they think about combustion reaction. You can get as we see here, here's a combustion reaction. Again, organic guy, carbons and hydrogens, O2, always CO2 and water. It usually gives off some energy. You don't have to worry too much about, uh, what you make on the other side other than CO2 and water, like a combustion engine, like when you light a Bunsen burner, right? Those are all sort of combustion reactions. Heat and energy is usually sort of given off as a process of that, exothermic as well. Sometimes, though, those combustion reactions are what is sometimes referred to as an incomplete combustion. So if somebody says, hey, this was an incomplete combustion, really the only difference is you don't get CO2 out, you get carbon monoxide. Carbon monoxide, not good, poisonous type gas. Binds and not very good for us to wake up if you breathe too much of it. But really, an incomplete combustion basically is the same sort of reaction. The only difference is we don't get the full CO2 out. We do make carbon monoxide instead. Another type of reaction that happens with alkanes is a type of reaction which is known as a halogenation reaction. I spit it out. I know it's the last lecture. I'm trying to spit this stuff out. The halogenation reaction, and as the name implies, it obviously involves a halogen. So this is something like Cl2, Br2. We're adding that. Usually involves some heat or light involved in this reaction. And this type of reaction is what is referred to as a substitution reaction. So what happens in a substitution reaction with alkanes is pretty simple. You have an alkane, say like this guy here. And basically in a substitution reaction, a hydrogen comes off and a halogen goes on. So let's just say we had Br2. Now, what hydrogen goes off? If you look at all these hydrogens, they are all what are known as equivalent hydrogens, which means they're all the same basically. So you can basically take off any one you like. So if we were to do this, You could choose any one you like. We'll just say this guy here is going to come off, and only one of these BRs are going to come on in its place. And by the way, nothing really changes. So I'm running out of room. So I'm just going to redraw it over here. Everything remains exactly the same except for what you took off. So you could redraw exactly what you started with, exactly the way it looks like. So that looks exactly like what we started with. The difference is we took off this hydrogen and we put a Br in its place. Now, if you think about what came off with the hydrogen, which is going to be an H plus, and what was left over was another bromine, which would be a Br minus, and those two guys would come together and make HBr. So we would get these two things made, but this is the main thing here. And this would be 1-bromo ethane here, or bromoethane, really. We don't really need the number in this particular case. Any questions on that? So a substitution reaction, basically you take off a hydrogen and you replace it with something else. And again, usually you may be asked to draw only what is referred to as the monosubstituted product. And monosubstituted product is what it sounds like. You basically just take one hydrogen off. In reality, under the sort of right conditions, you in theory could let this whole thing go and replace all the hydrogens. But if you're asked to draw the monosubstituted, you would just draw one of the hydrogens gone. Again, heat, which is sometimes abbreviated with the delta symbol, HV, sometimes used up here as sort of a catalyst. But basically the same thing's happening. We're just going to replace one hydrogen is going to go off here, going to be replaced by one of the bromines coming on, and then our H and our Br would come together in that particular case. Any questions on the substitution reaction? So that's a certain type of reaction, which is again referred to as a substitution reaction. There's different types of substitution reactions, and there's mechanisms as to how this actually takes place. It just doesn't take place usually in a nice, pretty move like we just saw there. And that's what's referred to as mechanisms. And that's also something that you learn when you go to organic chemistry, the mechanisms as to how this all actually occurs. So sometimes we think, oh, it's just as simple as this pops off, this pops on. There's sometimes a lot of individual steps. There's a lot of steps where bonds are broken, new bonds are made, things kind of shift over. There's a lot of really interesting stuff that happens as these things sort of move around. The end result, though, is sort of what we're looking at here, but you'll learn if you do go on to take organic, a lot of these sort of mechanisms as to how these processes sort of occur almost in a step-by-step fashion where you follow where all the electrons sort of go and end up. Any questions on that there? Okay, so that was a good little bit about alkanes. So let's talk a little bit about alkenes as well and alkynes and some of the things that occur with those guys, just to make sure we get a nice little covering here. So alkenes and alkynes, as we talked about before, has a double bond, so that carbon-carbon double bond as the functional group. To our alkynes, we have a carbon-carbon triple bond. One thing that we should remember as well is, for example, if we look at an alkane, just to make sure, since we're tying into other things, if we wanted to know the hybridization of that carbon, this carbon would be sp3 hybridized, right? And that is a hybridization of an s orbital and 3 p atomic orbitals. How do we get that? Well, just a reminder, just to make sure, a very simple way to figure out hybridization is s, there's only one orbital, right? P's, there are 3, and D's, there are 5, right? Hybridization is related to electron pair geometry. And what that means is the total number of electron pairs around the central atom. And you do it like you do geometry, which means if you have a double bond or a triple bond, It only counts as one. So if we were to do this, this guy has one electron pair, two electron pairs, three electron pairs, and four electron pairs. So if you weren't sure what the hybridization is, you could always draw something like I just did here on the right. And you always start at the S and go, that's four. So that is one, two, three, and four. I use one s orbital and three p orbitals. That is sp3 hybridization. So that's a good way to sort of figure that out. Now, something happens different when we get into alkenes, which is our carbon-carbon single bond, double bonds. If we look at our central atom here in terms of electron pairs, it has one electron pair, two electron pairs, and double bond counts as only one electron pair. So when we get into our double bond situation, we have three electron pairs. That is our trigonal planar geometry. And if I wanted to know my hybridization of this guy, by the way, that's a bond angle of 120 degrees, as it says. If I want to know my hybridization of this guy, again, I could use my little chart here to figure it out. I have three bonds, so 1, 2, and 3. That is 1s and 2p, so this would be sp2 hybridization happening in this particular case. So we also get a different geometry when we get to alkenes. We also get what happens a lack of rotation. So in alkanes, because it's single bonded, you have freedom of rotation around that single bond, which is why in certain cases, you know, it's okay if you draw like the group up or you draw the group down. Once we add a double bond, even a triple bond to that, we are essentially locking everybody into place. We lose that ability to rotate because of that extra bond that's there. And everybody sort of locks into place and sort of loses that ability to sort of rotate. Um, any questions on sort of the hybridization part as well? As we talked about earlier, alkenes have a CnH2 times N sort of formula. And again, it's missing two hydrogens from the alkanes because it has, excuse me, it has made that extra bond. So it needs to lose those two hydrogens so it doesn't have too many bonds. Alkenes are named just like alkanes, except surprisingly, it ends with ene instead of ane. So if you had, say, ethane, and then you put a double bond like we're seeing here, that is what is known as ethene. This is sort of a common name for it. We'll do this. It is actually known as ethene, ene. And again, based off of ethane because of that. One important thing is when we were numbering and thinking about naming things with alkanes, it was the groups that were the priority. It is actually the double bond that's actually the priority here in terms of numbering. So when you would go to name some of these guys, and we'll talk about it maybe in just a bit here, you would actually number whichever way that would give the double bond the smallest number. So the functional groups always take the priority in terms of numbering. And when you have sort of the double bond here, that is sort of the functional group. So it would take the priority in terms of numbering. Here, you wouldn't need, in this particular example in the middle, you wouldn't need any numbering to indicate where the double bond's located because there's only one spot it can be. So there's no need for a number in that particular case. Alkynes, as well as our triple bonded guys. And again, with that triple bond, we do get a change in geometry as well. And our change in geometry, if we look at our carbon on the left here, we have one electron pair. We also have a triple bond, which only counts as one electron pair. And that means that we basically have two electron pairs. That is our linear geometry, 180 degrees. Now, in terms of our hybridization, again, you could do your little guy here. I got 2, so that is an S and a P. So that is sp hybridized on either side there. And in terms of naming, we also will lose an extra set of hydrogens from our alkene because we made that triple bond. Named the same way, except it ends in YNE at the end. So here's two carbons based off of ethane. It would be known as ethyne, YNE here would be the name. Any questions on that there? So some properties here of alkenes and alkynes, they're very similar to alkanes. They are essentially carbons and hydrogens. They are, as we talked about earlier, unsaturated. And again, what that means is they basically, because of the double bond or maybe the triple bond, they don't have the maximum number of hydrogens, because again, we have to get rid of basically 2 hydrogens for every bond we lay down. So when we drop that double bond in there, got to lose a hydrogen. Triple bond has to lose another 2 hydrogens. They, again, because of their nonpolar sort of aspect of it, going to probably be using dispersion forces. And again, as we talked about earlier, that is relatively weak, and we would expect low melting points and boiling points as well. They will also probably be insoluble in water because of that. The multiple bond is always drawn in a condensed structure. So as you can see here, you do have your double bond drawn in. Also drawn in line structure as well. So we would have a double bond drawn in like that. You could even, have a triple bond drawn in like that. We name it ENE and YNE. So to give you an idea in terms of naming, we'll name the 2 that I just kind of drew really quickly there. We would want to follow the same approach as what we did with alkanes. We want the longest continuous carbon chain. The difference is here, it does need to contain the double bond or the triple bond in this case. So if we did this first one I drew, that is 1 carbon to 2 carbons, to 3 carbons, to 4 carbons, to 5 carbons. So that is 5 carbons based off of pentane, because it's 5 carbons. I have a double bond happening here. So my ANE then becomes pentene, ENE, because of the double bond. Now, remember, as I said before, once you get to about 3 or 4 carbons, or really 4 carbons or more, if there are multiple options as to where the double bond could be located, you do need to give the location of the double bond. And we want to give the double bond the smallest number. So if I numbered left to right in this particular case, this would be carbon 1, this would be carbon 2, this would be carbon 3, that would be carbon 4, and that would be carbon 5. That means going in the red direction, my double bond is at carbon number 1. I'm assuming we're not going to be able to beat that, but just to show you we cannot beat that. If I went the opposite way, this would be carbon 1, this would be carbon 2, this would be carbon 3, this would be carbon 4, and this would be carbon 5, which means going the blue direction, my double bond would be at carbon number 4. So just like in organic chemistry, we want everything small. We would want to go the red way, and this guy would be known as 1-pentene. The 1 is where the double bond is located. It starts right here at carbon number 1. Any questions on that? Now, if we look at our guide to the right, again, doing the same approach, longest carbon chain that contains our triple bond in this case, 1, 2, 3, 4, and 5. Again, we're going to get a guide that is based off of pentane, but we have a triple bond. So pentane becomes pentyne. And just like the other way, or the other guy, we want to give the location as to where that triple bond is located. So we do have two options. So we could go 1, 2, 3, 4, 5, or we could go the other way, which would then be 1, 2, 3, 4, and 5. Going in the red direction, my triple bond starts at carbon 2. Going in the purple direction, my triple bond starts at carbon 3. So we would want to go the red way here, and this would be 2-pentyne, 2 for the location of where you find the triple bond. Questions on that there? Now, if I had things attached to it, we would do the same thing. So let's take my guy I drew here. Let's do that. And heck, let's just put a guy like that. All right, so we basically got the same thing that's happening here. We got our longest carbon chain, hopefully, unless I just messed it up by doing that. Let's just see. We have 1, 2, 3, 4, 5. We could go 1, 2, 3, 4, and up to 5. So 5 looks like the longest still. So 1, 2, 3, 4, and 5. We again are going to have the base of our name being, and we already know if we number this way, 1, 2, 3, 4, and 5, that the base of it is 1-pentene. The 1 again for the location of where my double bond is. But I do have another group attached, which is a methyl group. And because I have to lock in numbering left to right because of the double bond takes the priority here because it's the functional group. That means that my methyl group will be at carbon 4, and this would be 4-methyl. I'll try to squeeze it in there. 1-pentene. So 4-methyl 1-pentene. So once you kind of lock into place in terms of which way you have to number to give either the double bond or the triple bond the smaller number, every other group that might be there needs to be numbered accordingly. Any questions on that there? So if we look at these couple guys here, so if we look for our longest carbon chain that contains the double bond, 1, 2, 3, 4 going straight across, 1, 2, 3, 4 going straight up. So longest carbon chain with our double bond is here. That is 4 carbons, has a double bond, so it goes from butane to butene. We do need to give the location of our double bond, and numbering left to right will give us the smallest number. And that means that our double bond's at 1-butene, and that means that our methyl group is at carbon 3. So this would be 3-methyl 1-butene. Any questions on that there? Going to our guy to our right, we got 1, 2, 3, 4, 5, 6 carbons in a row with our triple bond. Only other option would be maybe start up on top, 1, 2, 3, 4, 5, 6. So you get 1, 2, 3, 4, 5, 6 a couple of different ways. So might as well just take the straightest, easier to see that way usually. So that is 6 carbons with a triple bond. So 6 carbons is hexane. Triple bond makes it hexyne. Location of the triple bond, you could probably see that if you go 1 and 2 this way, that gives it the smallest number. So that's going to be 2-hexyne for the location of the triple bond. And the group that we have up here is an ethyl group. And because we were locked into numbering right to left because of the triple bond, our ethyl is at 4, and this would be 4-ethyl. That's a dash between the 4. 4-ethyl-2-hexyne. Any questions on that there? Okay. So that should take us through our naming there of that. All right, that's good. They agreed. So why don't you name these guys here? Why don't you give the name and then also why don't you draw the line structure here for these guys? So take a minute or two, see what you come up with. So 4 in a row is butane. Double bond makes our butane become butene. We do need to give the location of that double bond, and it looks like it should be at carbon number 1. So this is 1-butene. Line structure for that guy would look something like this, and a double bond happening right about there. Looking at their second one, also 4 in a row, also a double bond. That would be also butene. Difference though is we went left to right, double bond at carbon 2. We went right to left, double bond at carbon 2. So that is 2-butene. And that is also why we do need to give the numbers, because as you can see in the first one, the double bond's at the first carbon and the second one is at the second carbon. That way people know exactly which one you are talking about, and our line structure would look, in this case, something like that. Coming here, longest carbon chain in a row that does contain the double bond is also 4. You could get it 2 ways, but might as well just go the straightest here. So this is also going to be butene. Now, in this particular case, if we went 1 and 2, 3 and 4 are 1, 2, 3, and 4. In terms of the double bond, it does not make a difference which way you number. The double bond is always going to hit carbon 2. So sometimes this happens that you get a tie, if you will, for the double bond. It doesn't really matter. But what the next important thing would be is the actual group. And it does matter for the group, because for the group here, which is a methyl group, if I numbered left to right, that methyl group would be at carbon 3. But if I numbered right to left, it would be at carbon 2. And because it did not make a difference for our double bond, we would actually want to go in this direction here. And this would then be 2-methyl 2-butene. So sometimes you do get sort of a tie, like we just see here, that, in terms of, say, double bond, triple bond, later on OH groups, things like that, it doesn't really matter, which way you go in terms of that. You'll get the same number. If that does happen, then what you want to do is go to the next important thing. And in this case, it would be the group, and number whichever way would give that group the smallest number. Questions on that there? Lastly, here we got 4 in a row, but we have a triple bond happening. So that's going to be our butane. And again, 1 or 2, 1 or 2, 2-butane. And again, to draw some of these Lewis structures here, we would have that happening. And carbon 2, and something like that. So that would be this guy. And then this guy would just be triple bonded like so. Question on those there. Okay, so we have a few more to goes, but we've been sitting for a little bit. So why don't we just take a 10-minute break, and we'll come back, kind of finish up the rest of it, and we'll talk about the final and all that good stuff. So just give everybody a chance to kind of stand and stretch. So I'm just going to keep it rolling and stuff like that. And then about 10 minutes, we'll pick back up. So about 1:20, I think. And that way you can kind of stand, take a little break. I'm going to do the same thing, I think, and we'll pick back up. But I'm just going to let everything run. So we'll be logged in, and that way we'll just pick back up. So I'll see everybody in about 10 minutes, and we'll continue. We'll wrap up the rest of this conversation about organic, and we'll finish up taking care of all the other business that we need to do. Okay, so hopefully you got a chance to stretch a little bit, and we're just going to kind of finish up the last bit of this and finish up really the semester, I guess. First off, any questions on stuff we've been talking about up to this point? Okay, so we were just talking about naming these guys. So why don't we do a couple where we draw structures from the name just to kind of see how it works when we have double bonds or triple bonds involved. So what we'll do is maybe, let's see here. We'll skip these examples, but we'll just use the page here. Why don't you draw 3-ethyl, 6-methyl, 3-heptene, and why don't you draw, let's see, 2-bromo, we'll do that one, 2-bromo, um, 3-hexyne. So draw. Let's do both. Why don't you do both the condensed and why don't you do the line formula for both of those? So take a minute or two and draw both of those guys. So 3-ethyl, 6-methyl, 3-heptene, 2-bromo, 3-hexyne. Again, works the same way. You want to kind of work backwards in terms of the name and drawing it. Okay, so let's take a look at this one. We'll start with the first one. So we're going to work backwards. So heptene, that tells us we have 7 carbons. The ENE tells us we have a double bond there. So we'll start with that, 7 carbons. 5, 6, and 7. Has a double bond at carbon number 3, which is what the 3 stands for. So again, because you're drawing, you could go either way on that. So I'm going to go left to right. So carbon 1, carbon 2, carbon 3. That is where my double bond's going to be. That takes care of that part of it. Because I went left to right, I got to keep with that numbering. And that means at carbon number 6, 1, 2, 3, 4, 5, 6, there is a methyl group. Again, also meaning I just got to continue left to right in terms of my numbering. That means at carbon 1, 2, and 3, there is a ethyl group, which is a 2-carbon group. Everything else, just like we did with the alkanes, going to be hydrogens until we get to 4. So we need a couple there. This guy needs just 1. This guy here with the double bond needs none. This one needs 2, and this one needs 3. Any questions on the condensed one there? Our line structure, again, we could follow kind of the same procedure. We'll start with our base of 7 carbons. I guess I should count 1, 2, 3, 4, 5, 6, and one more makes 7. Again, we could go left to right. So 1, 2, and 3, which means my double bond would be there. Again, let's see here, 6. So 1, 2, 3, 4, 5, and 6 is where my methyl group would be. So again, we could just lay a line up. And lastly, 3, again, continuing with our same numbering pattern, 1, 2, and 3, we have an ethyl group, which would be sort of a 2-carbon group, something that looks like that. Question on that particular one there. That then leaves us, what we have there, 2-bromo, 3-hexyne, I think. 2-bromo, 3-hexyne. And same sort of pathway here. We have hexane basically, which is 6. YNE tells us a triple bond. So we'll start with our base of 6. Triple bond at carbon number 3. I am again going to go left to right. You could go right to left if you wanted to, but I'm going left to right. 1, 2, and 3. Again, going to make that a triple bond. That takes care of all of that stuff. Keeping my numbering left to right, that means at carbon number 2, bromo would be a bromine, and everybody else here going to be hydrogens. That guy needs none. That one needs none. This one needs one. And this one needs three. Again, line structure, we'll start with our base of 6. 1, 2, 3, 4, 5, and one more makes 6. Going left to right, 1, 2, and 3 will be our triple bond. And keeping left to right, number 2 would be our BR. Any questions on drawing these guys? So very similar sort of process. Honestly, all organic chemical guys are similar to that process. Always good if you have the name, go backwards. And like I said, actually, I think probably the easier of the two. Any questions on naming, drawing those guys, any of those things? Okay. Let me get back to where we were. Let's see here. Let us go here, I think. Yep. All right, we'll pick back up here. The other one was another more naming, and we kind of did that. So another kind of important aspect of sort of that double bond that occurs is another type of isomers that develop. And we did talk a little bit about cis and trans isomers when we talked about coordination chemistry. Again, a reminder that when we talk about cis, it means the same side. And when we talk about trans, it means opposite sides. And unlike sort of coordination chemistry, what we're talking about here really is the double bond. So we're talking about two groups on opposite carbons in a double bond where they're either on the same side of the double bond or on the opposite side of the double bond. And these develop really because of what I was talking about earlier, that when you have a carbon-carbon single bond like you do in an alkane, you have pretty much free rotation about that single bond. So, you know, those groups are free to travel all about. Once you introduce that double bond, it sort of locks everybody into place and you lose that lack of rotation here. So you lack that rotation that can occur here. And what that does is it really locks people into place. So it locks everybody into place as either being kind of, you know, on one side of the double bond or another, because you really don't have that free rotation. So when we look for cis or trans isomers, really the important part to focus in on is actually the carbon-carbon double bond. So you would want to focus in on this carbon-carbon double bond. And there's a couple important things to see. First off, you want to look on opposite carbons and find two groups that are the same. In this case, the CH3s are the same. Also, the hydrogens are considered groups in this sort of situation. They're also the same. They're on the same side of the double bond. Both of the CH3s are above the double bond, and that would be the cis isomer here. While if we look at the double bond in our second one here, we have the CH3 group above it, and we have a CH3 group down below it, opposites of each other, and this would be our trans isomer here. Now, they're isomers because they're the exact same guy, basically. They have the exact same name. The only difference is whether you put cis or trans in it. So when we look at something like this and we want to name it, also really important to give it the correct name. So if we were to name this guy, there is one carbon here, there is two carbons here, there is three carbons here, there is four carbons here. Very often people look at just the carbon-carbon double bond and go, oh, there's only two carbons. But the longest continuous carbon chain is actually all the way through here. All these guys are carbons. That's four carbons. And really probably should have scribbled all over it so I could actually see it. There we go. We'll get rid of some of this stuff so we can actually see it. Here. So if we look at that again, our four carbons run all the way around here. and 4 carbons is butane, it becomes butene because of the double bond. Location of the double bond is the second carbon. And because it's a cis, people will add cis in front of it. So they'll call it cis 2 butene. Very often, like I said, people just look at that double bond in the middle, go, oh, there's only 2 carbons. This is like 1 methyl, 2 methyl ethene or something like that. But this is the longest continuous chain. Same thing happens on the guy on the right if we look to name it. If we look to name it, again, longest continuous carbon chain, 1, 2, 3, and 4. Also, again, going to be butene. Double bond also, again, at the second location. Difference is this would be trans 2 butene. So these are isomers. They are locked into place because of the lack of rotation that occurs because of that double bond. And we end up with these isomers, which are known as cis or trans isomers. Any questions on that? So as we can see here, again, here's some examples of those isomers. But how do you know you can have a cis or trans isomer? There are actually a couple of rules that you have to make sure of in order for even a cis or trans isomer to happen. The first rule is, hey, you probably need a double bond, obviously. So when you look at the carbons in that double bond, on the same carbon, the groups that are attached, say A and B, they need to be different. They cannot be the exact same thing. Same thing on the other guy. The C and the D also need to be different. So you cannot have the exact same group on the exact same carbon in a double bond and have cis or trans occur. So they do have to be different. The other thing that needs to be the same is on opposite carbons, you need to have at least one group that's the same. And that could be something as simple as the hydrogens. It could be a carbon containing group, it could be chlorines, bromines, something like that. So the rule is when you look at the carbon-carbon double bond, each of the carbons in there must have 2 different groups attached to it. And then secondly, you need a group that's the same on opposite carbons. And then you determine, are those groups that are the same, are they cis of each other or trans of each other? Question on that there. So let's take a look at a sort of an example of that here. So again, focusing in here on our double bond. If we go to the right, this H and this ethyl group are different, so that's good. If we go to the carbon on the left, we have a hydrogen and a hydrogen. Those guys are the same. That is bad. So you cannot have no cis or trans is possible in this situation because we have the exact same group on the exact same carbon, that double bond. So that's what we were just talking about there. Question on that? So stereoisomers, and we talked a little bit about, I think, earlier and also in sort of coordination chemistry. These are isomers that differ only in their 3D arrangement. Constitutional isomers differ in the way the atoms are bonded to each other. So this is a constitutional isomer, different in the way that they are sort of attached. And then these 2 guys here, the middle guy and this guy, are stereoisomers, which differ only in their 3D arrangement. That's your cis and trans, but we get some different sort of guys here in terms of constitutional isomers. So whoops, I think you could see it, hopefully. Why don't you take a second and decide, could A, B, and C be a cis, a trans, or is it neither in those cases? And see what you come up with. Take a look here. All right, so I'm going to try my best to see it. It's kind of hard on mine, so hopefully it's better on yours. That's our carbon-carbon double bond, so we want to look at that. We want to first check to make sure that this group here, which is a CH3 and an H, those are different, so that's good. This isopropyl group here and our CH3 are different. So that is good as well. So now we need to make sure we have two groups that are the same on both of those carbons. And it looks like it is going to be our CH3 group here and our CH3 group here. And they are opposites of each other, which means that this should be trans. Any questions on that particular one here? Looking at our second one, we're going to look at the carbon-carbon double bond there. We have a Cl, which is different than a methyl, so that is good. We have this isopropyl group and this isopropyl group. That is the same group on the same carbon, and that means that we could have neither in this case. It is not possible because they have the same group attached. And in our last one here, carbon-carbon, hydrogen, ethyl group, it looks like, ethyl group on that guy, and hydrogen. So those are different groups. The group that are the same is our ethyls. They are on the same side. So that would be the cis in this particular case. Any questions on any of those? Okay, so why don't you take a look at a few more here that you I know can see at least, so that's good. All right, decide cis or trans in each of these, and while we're at it, why don't you give it a name, I guess. Actually, no, don't worry about the name. Just decide if it's cis or trans on each of these, or neither. Gonna go cis or trans or neither. So we're gonna focus in here on the carbon-carbon double bond. We got this guy and this guy, which are different, which is good. This guy and this guy are different, which is good. And we do have this one and this one, which are the same groups on opposite side, are opposite carbons, but they are on the same side of the double bond. So this would be cis in this case. Coming down here, there's our double bond. This guy and this guy, which is a group, are different. This one and this one's a group that's different. Our methyl group's the same on opposite carbons, and in this case, they are actually on opposite sides of the double bond. So that would be a trans in this case. And lastly here, if we look at this guy, this one and this one is different groups, which is good for cis and trans. We have a chlorine and a chlorine. That is the same group on the same carbon, and that is bad. So it can be neither in this case. Because of that, again, you won't be able to do the cis or trans. Any questions on cis or trans isomers? All right. So to sort of finish up talking here, let's talk about some of these common reactions that occur with alkenes. And alkenes, they actually undergo what are referred to as addition reactions. So earlier we talked about alkanes and substitution reactions. So in a substitution reaction, something comes off and something comes on in its place. In a addition reaction, actually both things come on. So in an addition reaction involving alkenes, what happens is if we just look at our alkene and we look at our carbons at this point, they basically have no place to add anything else. Both of those carbons already have 4 bonds. They are full. So when we do an addition reaction, what happens is we want to add something, maybe say 2 BRs. We need to make room for it. So what ends up happening is the double bond becomes a single bond, and everything stays the same. So you would redraw it just the same, but you would make the double bond into a single bond. The nice thing about that is now each of those carbons can accept what's coming in. So one of these bromines will end up here. The other bromine will end up here. And both of these guys, I'll put boxes and circles around it so you can see. Both of these guys have been added in, and this is why it's called an addition reaction. Both of those things get added in. If you remember in a substitution reaction only one of those guys actually came in. So that's essentially what happens here. And like I said before, there is definitely a lot more happening here than just that. And when you talk about mechanisms in real organic chemistry, you'll learn about really what is all transpiring to allow this to occur. But ultimately, what happens is we go from a double bond to a single bond that allows space for each of those to be added. And as you can see, one of the things is added to one carbon in the double bond, and the other guy is added to the other carbon. They're never added to the same carbon. So when that double bond breaks to become a single bond, one guy goes to one carbon, the other one coming in goes to the other carbon. So, they never end up on the same carbon. Any questions on that? That is what we see here with the hydrogenation reaction, like when they make margarine and stuff like that, partially hydrogenated. This is essentially what they're doing. They're basically taking those guys that have double bonds, adding hydrogen to it, and making them into basically single bonds. So same thing is going to happen here. This guy is going to go from a double bond. Double bond's going to break, become a single bond, and one hydrogen will end up here. The other hydrogen will end up over here as well. So we go from it really an alkene to an alkane. Usually requires some type of catalyst there to allow this to occur. And again, sort of an actual example here, our H2, again, double bond becomes single bond. Absolutely everything remains the same other than your double bond became a single bond. So to illustrate that, let me just kind of highlight those parts for you. This all here stays the same. That is all this right here, exactly the same. This over here and over here is this guy over here and over here. And again, double bond became a single bond. So everything remains the same. You just basically turn it into a single bond. And then one hydrogen comes in here and one hydrogen comes in here. And that again is our addition reaction that occurs. This is what is sometimes referred to as a symmetrical addition. And that's a fancy way of saying you really shouldn't screw this one up because you're basically adding two of the same. So you're adding two hydrogens. Sometimes you may be adding two halogens like Cl2, Br2, two Brs, two Cls. And that basically means all you have to do is break the double bond, make it a single bond, put one, say, Cl on one Cl on the other, one hydrogen on one hydrogen on the other. There's no really problem that happens in that case because you're basically adding the exact same thing. So if we look at sort of each of these here, whoops, it's a little all over the place. This platinum should actually be over here. It should be like an arrow happening there. This guy should be over here with an arrow. All right. So what's going to happen in this case, again, is the only thing that changes in this molecule is right here. Our double bond is going to become a single bond. And again, I'll just kind of draw it all the way out so you can kind of see all the bonds here. So when this happens, absolutely, positively, everything exactly the same. The only difference is I'm going to make my double bond into a single bond right there. But nothing else happens. Nothing weird happens. No rings start forming or anything crazy like that. And in this case, H2 is basically two hydrogens. So I'm going to add one here and I'll circle it so you can see that's the one we added. And I'll add the second one to the other one. This again is where our double bond was originally. And you basically just put it there. Same thing here. Basically, this is a carbon-carbon double bond. So in this particular case, we would just draw that. And that's what we would end up with. You may be asking what changed. Well, if we look at this carbon here, it actually has one hydrogen. This carbon here has one hydrogen to begin with. When we get rid of that double bond, that gives us room to add one hydrogen here to go with our original hydrogen that was there. So I don't know, I'll just circle these two. We added these two hydrogens in that particular case, and we ended up obviously with something with no double bond. Any questions on that there? Now, sometimes you don't get a symmetrical addition. You get sort of an unsymmetrical addition, and sometimes, you do end up with two different things that you're adding in. So instead of two Brs or two Hs, you may have hydrogen and something else like HCl, HBr. You may even have water, which is like H and OH. And in that case, you're actually adding two different things. And this is sometimes referred to as an unsymmetrical addition. And there are actually rules that happen when you do these type of additions. In this case, we're adding water. This is a weird way of showing water, but water can be thought of as H and OH. And this is what is referred to as a hydration reaction. And basically the same thing occurs here. Our double bond will become a single bond, and hydrogen will go to one carbon, OH will go to another. And what we make is we go from an alkene to an alcohol because of the OH group that's there. This usually requires a strong acid like sulfuric acid as a catalyst in this particular case. If we take a look here, here's an actual example one. Again, our double bond going to become a single bond here. And again, nothing's really going to change. So if we just kind of highlight the parts, all that is right here. All of this is right here. And again, our double bond here became a single bond. That's going to allow room for our water to add, and water will add as H and OH. So H over here, OH over here. We go from ethene to ethanol, which is an alcohol, OL, because of the OH group. And this is a hydration reaction in this particular case. Any questions on that? Now, there is one that's referred to as an unsymmetrical addition, and this occurs when we are adding something, H and something else, where there is different numbers of hydrogens on this carbon-carbon double bond. And what I'm talking about is the number of hydrogens that are directly attached to the carbon. So in this case, there's one hydrogen and two hydrogens to begin with. On the carbon on the left, there is only one hydrogen that's directly attached. Remember the CH3, the carbon is actually attached here. So the connection is this, right? So there's only one there as opposed to here where there are two directly attached to it. So in this situation where you have different numbers of hydrogens attached and you're adding something that is different, so not two things that are alike. So again, here's going to be H and OH being added. This is an unsymmetrical addition, and basically the rule says that the hydrogen ends up on the carbon that had the most hydrogens to begin with. That is Markovnikov's rule. We'll see his name in just a second. So that's a lot of wording to tell us that when we add the hydrogen in here, it really should end up on this carbon because that one had more hydrogens to begin with. And that's what we see here. This is what is sometimes referred to as the major product. If you did the opposite, this is what is sometimes referred to as the minor product. And usually you're interested in the major product, which would be this guy. And we get the same thing happens. Double bond becomes a single bond. The difference is we're going to add our hydrogen specifically to the one that had more hydrogens to begin with, and the OH would end up on the other guy. And again, that would give you your major product in a reaction such as this. Question on that there. And determine which of the two products we use. Markovnikov rule, and that's basically it. He did a lot of work with sort of these things and electrolytes, and he found that basically there's sort of a pattern that the hydrogen ends up on the one that started with the most hydrogens in the double bond. So that's sort of the rule that we do want to follow here. So again, similar situation as we talked about here. This first carbon here has 2 hydrogens. Carbon on the left has only 1. So as we just saw, really the major product is going to happen when we add that hydrogen to the one that started with the most, and that will give us our major product in that particular case. Any questions on that? And it also works for things that are not water, like HBr, HCl, kind of works the same. Why don't we just do these guys here? So why don't you try to draw the products of each of these and see what you come up with. So take a moment or two and see what happens. Then we'll go over it. Almost your product's going to look like. So I'm just going to draw this exactly like they gave me. Again, I'm going to make it change just a little bit. I'm just going to make a double bond here, and I'm just going to kind of draw a little straighter than they have it. But you could draw it exactly like it was, right? And in this particular case, absolutely nothing else changes along the way. We're adding H2, which is 2 H's. And this is a symmetrical addition, which means really, we can't mess it up. We just need to put an H on one and an H on the other, and that would be it. Again, basically double bond becomes a single bond, and you add both things in, one to each of the carbons in that double bond originally there. Any questions on that one? Same sort of thing happening. I'll go to C first. Same sort of thing happening here with Br2, basically, right? So that's basically what that is. I know, again, this entire thing here is going to look exactly the same, except I'm going to turn my double bond into a single bond. So I'm going to also, again, just draw it slightly different, but nothing's really changing. I'm going to draw my CH3 up and my other CH3 down on that guy. I'm going to make my double bond into a single bond. And I then would have an H and a CH3. And again, you could draw it exactly the way it looks and just make it single bonded if you wanted. This way, I know I could just put my 2 BRs on the ends if you like. And we will end up with something that looks like that. Any questions on that one there? Okay. Now, let's try this one more time here. We'll go with this guy. So I'm going to, again, know that it's really just where that double bond is located that's going to change. So I'm going to redraw this entire thing just the way it was. And I'm just going to try to figure out where would be a good place to do that. I'm going to try to go above it, I think. So again, I'm just going to kind of just slightly rotate some things. I'm going to have my CH3 and my C, and that has another CH3 attached to it. That is where my double bond is. It will now become a single bond to a carbon that is attached to a hydrogen and a very long group, which looks like CH2, CH2, and CH3. Okay, we're adding water, which is H and OH. So what we want to know, though, right, is when we look at this carbon that was in our double bond, and I'm just going to kind of accentuate it up here. That is CH3, carbon, CH3, double bond, carbon, hydrogen, and my other long guy there. Originally, right in this double bond, the carbon on the left-hand side has no hydrogens. Carbon on the right-hand side has 1 hydrogen attached. So if you remember, Markov-Nikov's rule is the hydrogen that I'm going to add should go to the carbon that had the most hydrogen to begin with, and that's going to be this guy right here, while the OH would go to our other guy, which would be this guy right here. I'm hoping you can still hear me. Yes. All right. I'm hoping. All right. And that's what we would end up with. Same sort of thing will happen on our bottom guy here. We will end up with uh, our CH3, our C. Again, nothing much changing here. I'm going to make my double bond into a single bond. And same thing here, the H that's going to be added will go to the guy on the right because he started with 2 hydrogens. The Cl would go here. Any questions on that? All right, that officially I hope you enjoyed the class as well. It wasn't too bad. We do have a couple of things to go. So a couple of things happening here is we have one more lab, which is the organic lab. I'm going to put it up as soon as we're done here. It will be due by the end of next week. And it kind of goes over a lot of the stuff that we talked about here. So there's going to be a module. I'll have you, I think, go and look at some or make some molecular models using sort of an online sort of thing. So it should be pretty self-explanatory. It'll be due towards the end of next week, or the end of next week, really. I think Friday is what I put on it. So you make sure that you do complete that. It is worth points, so make sure you finish. Other than that, in terms of lab, I don't think we got anything outstanding at this point other than that. So make sure, again, that you do complete it by the end of Friday, I think, of next week. That does bring us to next week, which is finals week. And again, a reminder, hopefully you remember, but we do have 2 finals. We do have a lab final, which is worth 5% of your grade. And we do have a lecture final, which is, I should remember, but I want to say 20% of your grade. I could be wrong there. That seems right. Just to make sure, I think it is 20%. Thank you. Usually sounds like the right number there. So it is 20% of your grade there. So, we got about a quarter of your grade still out next week. So I would highly recommend not missing any of those things, right? No makeups or anything like that. Make sure you're ready to take it and all that good stuff. Let's just talk about when it is. The lab final is it is actually going to be Tuesday. So we'll have it on Tuesday, and that is 12/8/20, and it is from 10:30 a.m. to 1 p.m. So the lab final will be like it sounds. It will cover the lab component. So it will cover everything from, just basic lab safety, proper glassware, molarity. It will cover things like the experiments and maybe similar calculations or something like that. So maybe you might be given some data. And it has to do some similar type calculations like we did in a lot of these labs throughout the semester here. So it will kind of cover a little bit of everything in that sense, everywhere from, even though, again, we weren't necessarily in person, but we did, I think, had a whole thing about lab safety, right? So, there'll be questions on that. And then also, like I said, it'll be more geared towards, I would say, the lab part of it. And maybe you're given information more like you did in an experiment, and maybe you have to solve for something, or maybe some theory behind using some equipment, or the idea of doing some type of experiment, in the context of the experiments that we did this semester. And so obviously what we talked about in those things. I would say out of the 2, the lab final, usually you're in pretty good shape. If you were, halfway conscious through everything we talked about for the labs, and you did the labs, and probably you'll be in pretty good shape if you just study for the lecture final. It will cross over. Obviously, the topics are the same. But again, it'll just have a little bit more of a sort of lab focus, I guess, than the lecture final. It probably will be shorter in terms of I don't want to say questions, but maybe shorter in terms of work and that type of stuff than the lecture final and stuff like that. So the lab final will be the same format. It's a very good question. I haven't really truthfully written it yet. I do think it will be a similar type format. There might even be a little bit more. Um, there might be some multiple choice type questions as well, and there might be, obviously, like I said, some of those lab questions where maybe you're given some data and you have to do some calculations and show your calculations. So not 100% exactly the format. I'm trying to remember kind of, what I've done in the past, but I'm thinking it will probably be some combination of that, maybe some questions which are maybe just more, pick the right answer sort of thing, like a multiple choice sort of part. And then there might be some sort of problems maybe where you have to kind of show some work and, that type of thing would be my guess. Other questions on the lab final? Okay. So you'll have that entire time, and just so we were clear, in terms of finals, you are expected to start at 10:30, and it is only going to be open during that time period. Again, even though we're sort of online, we are sort of a synchronized class, which means I believe the school and everybody expects us to adhere to our final schedules as well, so there's no conflicts with any other classes you may be taking and stuff like that. So it will, really happen during that time period. So it's not just like a recommendation, maybe it's going to happen during that time period. We're actually, I believe, unless I misunderstood anything, but I don't think I did, we're really supposed to sort of maintain that sort of final scheduling, again, to avoid any sort of conflicts that might occur with other classes that you may be taking as well. So our lab final is at 10:30, so not too bad. Actually, a little bit later, so you get to sleep in as well. Um, no, so we're not going to meet next week. So this will be it in terms of us sort of meeting. So just like finals, really, you just come and take the final. So since we have sort of the computer proctoring happening and we're not together in a meeting, we actually won't meet as well next week at all. So you'll just at like 10:30 a.m., kind of like a normal exam, there'll be an announcement that will come out that says, hey, the final's open. At that point, obviously using proctorial and everything else that we've been doing for our other exams, you can log on, take it through Canvas and submit it. And then that will be it, obviously, for that. So yeah, so you just will just begin it when it opens. Um, Other questions on that? Yeah. So again, like I said, the lab final, I think if you studied for the lecture final, you'll probably be okay for the lab final. And again, like I said, if you have sort of an understanding of the experiments that we did, sort of the reasoning why we did some of the things in those experiments, why we use some of the sort of procedures, some of the calculations obviously involved in those, you should be in pretty good shape for that. Okay, that also means that our lecture final is on Thursday, it looks like. So at least we have a little break between the 10th. And that one is 7:30 a.m. So you got to sleep in a little bit on Tuesday, but you got to wake up early on Thursday to 10 a.m. as well. And again, it really will be during that time period, and for the same reasons I just spoke. So you don't get any type of conflicts or anything like that. I believe everybody's supposed to sort of maintain the normal sort of final schedule, so you don't run into, I got this final happening at the same time. So obviously you should be in our class during these time periods usually, and you shouldn't really have anyone in schedule, hopefully a final at the same time. I don't think that should be happening. And that's why, so it really will open at 7:30, and you'll have until about 10 a.m. I may leave it open a little bit longer if you want, but I'm not sure. I haven't really decided, but officially that's sort of the time period there. And same thing, we won't meet on Thursday either. You'll get that announcement like a normal exam, and it will obviously open up. You'll take it using proctorial and all that kind of stuff like we've done before. It will cover everything that we talked about, so it will be comprehensive through all the chapters. So we started at, what did we start way back when? We started at 12, which was kinetics. Then we went into equilibrium, which was 13, acid and bases on 14, solubility, complex ions in 15, thermodynamics in 16, electrochemistry in 17. We did not do 18, so we went to 19 after that, which was coordination chemistry. And then we finished up here with 20, which was organic, like we talked about today, and 21, which was nuclear chemistry as well. So we had a test on most of those chapters, except for, I think, 20 and 21, if I'm not mistaken. And so everything will be fair game. When I write the final, I'm not going to necessarily focus more on one thing versus the other. But I think it will usually end up being fairly comprehensive over everything. So you want to think about the big stuff that we obviously talked about during this semester. So clearly kinetics was big. Clearly equilibrium was a big topic. Obviously titrations, buffers, those were pretty big topics. Galvanic cells was a good topic. All that nuclear chemistry stuff that we talked about earlier in the week. Those are some big sort of topics that you want to sort of think about. In terms of, in terms of organic, I'm going to say for organic, just to kind of narrow it down a little bit, which is the one we talked about today. I think what you'll need to know is basically the stuff about alkanes. So how to name and draw. You need to obviously know the first 10 alkanes, their names. And then obviously you need to be able to do some of the naming like we did today as well for alkanes only, not alkenes or alkynes, just alkanes. You also need to know, that. Functional groups, that's what I was trying to think. Thank you. Functional groups. So although you don't need to know how to name all the different ways for the other sort of thing, you need to be able to recognize functional groups. So just that part out of this chapter that we talked about today. So again, you need to be able to obviously know what alkanes are. You need to be able to name the first 10 alkanes. You need to be able to name guys properly, like we did, like 1-methyl, butane or something like that. You need to be able to name something like that. You need to be able to draw line structure, condensed structure if you're given the name, and you need to know the different functional groups for the different organic compounds, which should, I believe, be a table as well in your book in addition to what we talked about today. So no need to worry about alkenes or alkynes or any of that cis or trans or that stuff that we just talked about here towards the end. So we'll kind of narrow it down in terms of organic of those things. Any questions on chapter 20, what you need to know? So basically it's kind of like the alkane part basically, and how to name and draw and just what the different functional groups are, be able to draw them, recognize them for the different organic compounds. Any questions on that? So if I had to say, see here if this will work, maybe. Just roughly taking a look. I would say probably from like this slide forward, probably is all that alkane stuff. So, before this slide is kind of what you're responsible for. Anything after sort of this slide, you probably are okay and don't have to worry about it. Any questions on that? So where am I writing here, right? Okay, so like I said, it will cover everything. Anything that you are normally given on one of those exams, you will be given again. So any type of constants, obviously you'll be given again. Any type of, conversions that you need, anything that comes from a table, You'll be given like normal, obviously a periodic table as well. So, anything, if you look back on like your other exams that were sort of provided for you, will be provided for you as well. And that includes obviously constants and values and stuff, rather like say chapter 21, the nuclear chemistry, things like, like the 931.5 mega electron volts as an AMU will be provided for you. The mass of a proton, neutron, and that type of stuff would be provided for you as well. Um, Anything that you were kind of responsible to know on other exams, like formulas and stuff like that, you're still responsible to know. And again, just so we're clear, it is a closed note book exam. Shouldn't be out at all notes or anything like that while you're taking the exams, for both the lab final and the lecture final. So they're both, everything is closed notes. Yeah. Any questions on the lecture final? The lecture final will be a similar format as the other exams for sure. So it probably will be mainly problem based, I would think. But there may be some multiple choice type questions as well. But I think more so it'll be probably very similar to our previous exams in terms of format, the lecture one. Any questions on that? Anything going on or anything like that? Okay, other than that, like I said before, oh, good question. Yeah, homework. So in terms of homework, we did, what did we do? We did, what was our last test? It was on through 19, right? I believe. Or was it not 19 on that? Whatever it was. Yeah. Let me see here. That last exam was 16 and 17, not 19, correct? Yeah. So you need to turn in homework for 19 and 21, I think would be good. Chapter 19 and 21. You should also obviously do some homework out of 20, but you don't have to turn it in. So the only two that need to be turned in will be these two. They'll be due on, we'll call it the end of the week as well. We'll go Friday for this one as well. That I guess would be the 11th. So those two chapters will do. You don't have to turn in chapter 21. I would recommend that you do some of that stuff, but probably if you do the lab on the organic, that probably will help you for that chapter, I think. So since we did have 19, I think still out there as well in 21. So 19 and 21 will need to be turned in by the end of the week next week, not this week, but the end of the week next week. And I would also recommend probably doing those questions before the final as well, because those chapters will be on there. So again, we had a test on everything except for these last three chapters. So probably doing those homework would be a good idea. So you just need to turn in 19 and 21. You don't have to turn in 20. You'll get credit for 20 if you take the final, but you should turn in probably 19 and 21. Other questions? Okay, so like I was saying before, thank you very much for listening to this kind of long lecture here. Again, I hope you enjoyed the class, enjoyed having you in here. Um, I wish you the best of luck on our finals as well as your other finals. Have a nice break as well, good holiday season. And again, if you do need me for anything in the next week or so, you could always email me and stuff like that. I'll be happy to get back to you. And again, on both Tuesday and Thursday, there will be no Zoom meetings or anything like that. It will just be like we normally take our exams. So again, the announcements will come out and you're expected to take it when it happens and it opens. Again, if you start too late and decide not to take it when it opens, this time you probably will run into trouble and you will definitely get cut off. And, whatever time you have left is the time you get. It will not be reopened. And most importantly, as well, make sure you upload your work after each of those things. Make sure that is the first thing that you do. It will not be accepted if you send it to me like the next day or something like that. All right. I say that because it just happened like yesterday. So make sure it doesn't happen to you. Make sure that after you submit your exam, you immediately upload your work. You do not definitely want to get zeros on all these problems on your finals and stuff like that. So make sure that you do not forget to do that. I'm not sure how that happens, but do not forget to do it. All right. Other than that, obviously, we are done, I think, for today and the semester as well. Um, have a good rest of your week and weekend. And like I said, if you do have questions, feel free to email me this week, throughout the week, the weekend, and stuff. If you have questions on something, I'll be more than happy to answer those for you. Have a good one.